Chemistry, the Central Science, Chapter 5, Thermochemistry, Lesson 1. So there's two main types of energy. We can talk about the categories of those particular types of energy, but we have kinetic energy and potential energy. So kinetic energy is the energy of motion, while potential energy is energy that is being stored or energy of position, right? If you're at the top of a hill on your bicycle, you have potential energy. As you ride your bicycle down to the bottom of the hill, the potential energy becomes kinetic energy. So it's always an energy transfer. We can change types of energy into others. The units that we use to express energy are joules and calories. So 1 calorie equals 4.184 joules. And just a little side note, a calorie that we talk about in chemistry is different than the calories that you read on your food labels. So those calories are actually kilocalories. So a calorie that we would calculate here, we would have to divide by 1,000, and then that tells you the amount of energy from your food. So how can we calculate kinetic energy? Well, we have to be given a mass and a speed. So this is a typical mass of a car in terms of kilograms. And I think this is, about 65, 70 miles per hour. So what is the kinetic energy of this car? Which means what is the energy that it would take to stop this car? So kinetic energy is 1/2 mass times velocity squared. And we always have to make sure that we are in units of kilograms and meters per second, because by definition, a joule is 1 kilogram meters squared per second squared. So I convert my speed, 88 kilometers, right? 1,000 meters in 1 kilometer. In 1 hour, there are 3,600 seconds. When I set this up, I want to make sure that kilometers are over hours. I don't keep that /hour on top, because then my conversion would be wrong. So 88 times 1,000 divided by 3,600 gives us 24 meters per second. I can now plug that into my equation, multiply everything through, making sure I square this first. I get a value of 424,512 kilogram meters squared per second squared. This is the same unit for a joule. And so we convert this into 2 sig figs, which, to show that explicitly, we would say 4.2 times 10 to the 5th joules. So that's how much energy it would take to stop this car. So what's the kinetic energy of an electron moving at 315 meters per second? So here we have a really teeny tiny mass, but we're moving a lot faster. Once again, our equation is kinetic energy equals 1/2 mv squared. So we have a mass here of 9.109 times 10 to the negative 31 kilograms. Multiplying by our speed squared, we get a value in terms of kilograms meters squared per second squared. We know that there are 3 sig figs here, so there should be 3 significant figures in our answer. So we can round 4.5192 to 4.52 times 10 to the negative 26 joules, because 1 kilogram meters squared per second squared is a joule. So not a lot of energy. The label on a food package indicates that it contains 215 calories per serving. So big C calorie is a food calorie. Little c calorie is chemistry calorie. How much energy is this in joules? So we have our conversions that say 1 little c calorie is 4.184 joules, and 1 big C calorie is 1,000 little c calories. So we set up our conversion to cancel out our big C calories into our little c calories to get to joules. So how much energy do we get from eating something that has 215 calories per serving? Well, we multiply everything on the top, divide by everything on the bottom. Rounding to 3 significant figures says 900,000 joules of energy are associated with this. To put that into scientific notation, to show the 3 sig figs, it would be 9.00 times 10 to the 5th joules. So this gives us more energy than the energy it took to stop that car. Think about that for a minute. All right, heat versus thermal energy and energy changes in chemical reactions. So heat is energy that is transferred. Heat always flows from a hot object to a cold object. It always goes that way. That is the spontaneous transfer of energy. Heat is not a measurement of thermal energy. Thermal energy is how fast molecules are moving in a particular substance. So the faster they're moving, the higher the temperature, the more thermal energy they have. Heat is a transfer of thermal energy. So things that are moving fast versus things that are moving slow, they slam into each other and we transfer the energy, right? Like hitting pool balls on a table, right? You hit one into the other, we transfer the energy. Sometimes they all move, but one moves slower. Sometimes one of them stops, but it's always a transfer of that energy. So it's kinetic energy, right? Things that are moving, slamming into other things. The faster object loses energy to the slower object gets a little faster, and the faster object gets a little slower. And this is a continuous process of how heat is transferred. So thermochemistry then is the study of heat in terms of chemical reactions. And we need to define some things, which is system versus surroundings. So system is what we're interested in. Surroundings is what is around it. So for example, if we're doing a reaction, let's say we're dissolving something in water. Well, the reaction of that substance dissolving would be our system. The surroundings would be our water. We can measure temperature changes in water. It's very convenient. So the total energy of the system and the surroundings equals the energy of the universe. So we need to talk about types of systems. Our first system is an open system, which means that heat can be exchanged and mass can be exchanged between system and surroundings. So we can lose heat, we can take heat, we can lose mass, we can gain mass. We can close the system, which then prevents us from losing any mass. So our mass would remain constant. However, in a closed system, we can still exchange heat. In an isolated system, now we can't exchange anything. So we've insulated it and we've topped it off, so we cannot lose mass and we cannot lose heat. Or gain heat, right? We cannot, there's no change. No change in mass, no change in heat. So thermodynamics is studying the change of thermal energy, right? Studying how heat processes happen. How do we exchange energy from the system to the surroundings? Dynamics means change. So we look at what we call state functions, and state functions are something that does not depend upon the path that was taken. So we have two hikers. One took a much longer path, one took a shorter path. So the path would not be considered a state function, right? The distance that was traveled would not be a state function because it depended on the path. However, they both started at the bottom of the hill and they ended at the top of the hill. So altitude or height would be considered a state function because it didn't matter on the path. It just mattered that you started at the bottom and you got to the top. Oh, it's like a Drake song. So change in internal energy, change in pressure, change in volume, change in temperature. Anytime you can put a delta symbol, which means change, that is a state function. Final minus initial, always final minus initial. Where did we start? Where did we end? What is the change in that? We'll see that we can look at change in enthalpy, change in entropy, change in Gibbs free energy. So anytime you put a delta in the front, it says I'm a state function. Path independent. So what is the first law of thermodynamics? It's very similar to the law of conservation of mass, which says we cannot create or destroy matter. Well, we cannot create or destroy energy. So this says that the energy change in the system plus the energy change in the surroundings equals 0. So we're not gaining, we're not losing. Or we simply say that the energy gained by the system is the same as the energy lost by the surroundings, or vice versa. So in looking here, if we're doing a combustion reaction, which means that we have oxygen present, we are giving off heat from our system into the air around it. So that means that it's gaining the same amount of energy that's being lost. So energy is constant, mass is constant. We can interchange between mass and energy because Einstein told us so, E equals mc squared. But there's a fixed amount of mass and a fixed amount of energy in our universe. So looking at the first law in another form in terms of just changes in energy, what does this mean? Well, delta E is our state function, which is change in internal energy. Now here we have Q, which stands for heat, W, which stands for work. These are not state functions. How do I recognize that? Because there's no delta sign in front of them, and they're lowercase letters. Like, simply put, if you're a state function, you're going to be a capital letter and you get a delta, you get a triangle. So Q stands for heat, W stands for work. In terms of chemistry, we define work as a pressure volume, change in volume against a pressure, or, are we shrinking our volume because we're being compressed, right? Then the system is having work done on it. But the change in internal energy has to do with my transfer of thermal energy, right? Heat, am I gaining it? Am I losing it? And work, am I doing the work, or is the work being done on me? So what our sign values mean for delta E, Q, and W? Well, delta E would always be negative if work and heat were always negative, which means I'm losing heat and I'm doing the work. Delta E would always be positive if Q and W were positive. So I'm absorbing heat and work is being done on me. Now, of course, if our signs are opposite, then it depends upon the magnitude of both heat and work in terms of what would the sign be for delta E. But in terms of reading things and figuring out if work is done or you're doing the work, right? A gas expanding is doing work. A gas compressing is having work done on it. If heat is lost, then that's a negative sign. We're losing that amount of energy. If heat is gained, it's a positive sign. So we're gaining that amount of energy. So we can describe things in terms of being exothermic or endothermic. Exothermic means that we're losing energy to the surroundings, exiting the system, exo. So we give that a negative sign. Endothermic process means that we're gaining some amount of energy, gaining some heat. Endo meaning coming in. So that is a positive value. We're gaining that amount of energy. We're absorbing it. So when the system loses the heat to the surroundings, that's exothermic. When the system is gaining heat from the surroundings, that's endothermic. But the heat that is lost equals the heat that is gained. The heat that is lost equals the heat that is gained, because this is constant. The energy of the universe does not change. It is just a transfer. Calculations of internal energy. So this is having to do with calculating work, PV work. So nitrogen gas expands at a constant pressure. Calculate the work done if we're in a vacuum or against a constant pressure. So first thing we see here is it's expanding, which means nitrogen is doing the work, which means that we should have a negative value for that amount of energy. How do I know? Because I'm starting at a smaller volume, I'm ending at a larger volume. So my change in volume is positive. So I look down here and I first notice that this is not equal. This should be a negative or a subtraction sign. Work equals negative P delta V. All right, well, in a vacuum, my pressure is 0. There is no pressure. If there is no pressure, there is no work. It's just allowed to expand. So no work is done if you don't have a pressure to push against, or there's no external pressure on the system. So down here, we actually have a pressure, 3.7 atmospheres. This is a unit of a measure of pressure. Once again, I don't have the correct math here. This should be subtraction. So the difference, final volume minus initial volume, is 3.8 liters. Work says negative pressure times a change in volume. My PV work then is negative 3.7 times 3.8. Nothing cancels. I end up with work in units of liter atmospheres. And then I look up in the book and see that 1 liter atmosphere is 101.3 joules, because this is a reasonable unit for us to continue to work with in terms of energy. This is what we're going to do, joules or kilojoules. Negative 14 times 101.3 cancels out. And we get negative 1418 joules or negative 1400 joules. So that's how much work the gas had to do to expand 3.8 liters against an external pressure of 3.7 atmospheres. So just to be clear in terms of what work is and how we can define it with pressure volume work. So work is a force applied through a distance. That is the definition of it. Well, how is pressure volume considered work? Well, we keep in mind that pressure is simply a force applied over an area, right? That's what F divided by D squared is, where D is a distance. D squared means area, length times width. That tells me the area of something. Volume, I know, is length times width times height. So a distance cubed. If I multiply these together, then I see that I have a force times a distance, which is work. So this is why in chemistry we can talk about pressure volume work. Is a gas expanding? Is a gas being compressed? So in this instance, there's an external pressure. We see that it is expanding, so it has to do work against the surroundings, which means that we're losing amount of energy because we had a positive change in volume. If instead we were compressing the gas, so we were forcing the gas into a smaller volume, we'd see a negative volume change, and then there would be energy absorbed by the gas because the work was being done on it. Because if there's a negative volume change, then the negative times the negative becomes a positive. So we can't forget this negative sign, otherwise our work values will come out wrong. So delta E plus Q plus W, or delta E equals Q plus W. What is the change in energy if the work done to compress the gas is 74 joules while 26 joules of heat is given off to the surroundings? In reading these types of questions, the most important thing is simply identifying what are the signs associated with E, Q, or W. So it says work is done to compress the gas, which means that the gas is absorbing this amount of energy, which makes it positive. It says that this amount of heat is given off. If this is given off, then this means that this value is negative. So delta E equals Q plus W, I can plug in my values, add them up, and I see that my overall internal energy change is 48 joules. We identify this process as endothermic because the energy change was positive. That's it. All you have to do is look at the energy and say, am I positive? I'm endothermic. If I'm negative, I'm exothermic. So here we have a gas expansion. 87 joules of heat is absorbed, and the energy of the system decreases by 128 joules. So how much work was done? Well, once again, we're reading the language. 87 joules is absorbed. That means positive heat. The system decreases, the energy decreases by negative 128 joules, which means that this is negative. So delta E is negative, my heat is positive. So I plug things in respectively. Negative 128 joules equals 87 joules plus W. So then the amount of work that the gas had to do, which it was expanding then, is negative 215 joules. The overall process is exothermic because this is negative sign associated with delta E. So in terms of introducing this concept of enthalpy, energy, pressure volume work, so we know that delta E equals Q plus W. At a constant pressure, which we call isobaric, we have a term that we can introduce here called enthalpy. Delta H is enthalpy. Ooh, let's watch these things fly across the screen. Ooh. So delta H, which is enthalpy, depends on the change in internal energy plus amount of work that is done. If we use our terminology, our equations that say delta E equals Q plus W, and then we keep in mind that work is negative pressure times volume, I can plug that into where my W is. And I see that Q minus PV plus PV gives me just heat. So delta H is called enthalpy. So enthalpy is heat that is transferred under constant pressure. So that's what this little P here means. We're under constant pressure. So this is just a mathematical rearrangement of values, right? Enthalpy is a new term, delta H. Change in internal energy plus the work that's done. We simply plug in Q plus W here. We plug in what work is here. And then we see that the work cancels each other out. So under constant pressure, there's no work done. So we just see that for a particular reaction, delta H equals the heat that's transferred. If we're under constant volume, so now we have delta E equals Q minus 0, right? If there's no volume change, then there's no work being done at all. So delta E equals Q minus 0, which just then equals Q. So your change in internal energy equals heat under constant volume. So there's a difference between enthalpy and a change in internal energy. So we can see that these are different. The amount of work that is actually done over here is extremely minuscule. So, I mean, it's still being done. This is just a rearrangement of equations. But we just want to keep in mind that enthalpy changes are equal to heat that is transferred under constant pressure. And now we're done.